Welcome to The Explainer. I am so thrilled you're here today. Okay, let's just jump right in. Today, we're exploring a process that sounds honestly a little bit like magic. We are talking about joining solid pieces of metal together seamlessly without ever melting a single drop. It's a dive into the fascinating world of solid state welding. And this is a technology that's quietly revolutionizing everything from the literal coins in your pocket to the rockets we're sending into space. So here's our quick roadmap for today. We're going to cover 1, the joining problem, 2, solid state theory, 3, everyday solid state bonding, 4, friction stir welding, 5, the anatomy of friction stir welding, and finally 6, the future of joining. All right, let's start with that first one, the traditional joining problem. Section 1, the joining problem. When sparks fly. When we hear the word welding, this is exactly what pops into our heads, right? You think of blindingly bright arcs, intense heat, visceral sparks flying absolutely everywhere, and liquid metal dripping and fusing together. We call this fusion welding. The basic idea is simple enough. You melt 2 pieces of metal together, let them cool down, and boom, they form a joint. But as incredible as fusion is, relying on extreme heat and melting comes with some pretty serious mechanical and metallurgical baggage. And this comparison brilliantly illustrates exactly why engineers have been hunting for an alternative. On the left side, we see the major drawbacks of fusion welding. Look, when you melt metal, you drastically alter its microstructure. You introduce the risk of porosity, slag inclusions, and this nasty thing known as solidification cracking. Plus, it is incredibly tough to weld 2 completely different types of metals together, simply because they have completely different melting points. But now look at the solid state approach on the right. Solid state welding completely bypasses that liquid phase. Because there's absolutely zero melting, there is literally no chance for those fusion defects to form. It uses low energy, and you can seamlessly bond completely dissimilar metals together. It's a real game changer. So looking at the broader manufacturing universe, here is the family tree of joining processes. Over on the left, you've got your traditional fusion branches, arc welding, laser beam, oxy-fuel, the usual suspects. But if you track over to the right side of the tree, that's where you see the solid state branch. This includes mechanical, chemical, and electrical methods. We're talking diffusion, explosion, friction, and ultrasonic welding. These are an entirely separate class of manufacturing specifically engineered to keep metals in their solid form. So how exactly does this work? Let's unpack the core physics in our next section. Section 2, solid state welding theory, breaking down barriers. Okay, the absolutely crucial point here is the concept of adhesion. In theory, if you take 2 perfectly clean, perfectly flat pieces of metal and touch them together, they will spontaneously weld. The atomic attraction forces will simply pull them into a single piece. Wild, right? But in the real world, this magic trick doesn't quite happen when you say tap 2 spoons together. Why? Because of physical barriers. Things like surface roughness, microscopic contaminants, and invisible oxide layers covering the metal. The entire goal of solid-state welding is to overcome those barriers, using a precise combination of heat, pressure, and time to force those pristine raw atoms to touch. And once they touch, the bond is flawless. And again, because there is zero melting, you get zero solidification defects. Now, you might be thinking this sounds like some highly abstract experimental physics. Actually, scratch that. It's really not. Let's look at an everyday example. Section 3, everyday solid-state bonding, the U.S. quarter. Yep, that's right. If you have a U.S. quarter in your pocket right now, you are literally carrying around a perfect example of solid-state welding. Quarters aren't just one solid piece of uniform metal. They're actually a bimetallic strip created using a process called roll bonding. By forcing different strips of metal through these rigid rollers under massive, massive pressure, the process breaks down those oxide barriers we just talked about and achieves pure metal-to-metal contact. The metals essentially crush together into a single bonded sheet without ever getting hot enough to melt. It's such a brilliant, everyday application of this incredible theory. But while roll bonding is great for flat strips and coins, what if you need to build something larger and much more complex? Well, enter the crown jewel of solid-state technology. Section 4, Friction Stir Welding, the crown jewel. Invented back in 1991 by the Welding Institute over in the UK, Friction Stir Welding, or FSW, is an incredibly environmentally friendly green technology. It uses no external heat source, there's no filler material, and remarkably, it consumes only about 2 to 5% of the energy used in traditional arc welding processes. I mean, that is a massive reduction. It works in this beautiful mechanical choreography broken down into 3 really straightforward steps. plunging, traversing, and retracing.
So, visualizing these 3 steps, we start with the plunging phase. A rapidly rotating, non-consumable tool is pushed down directly into the joint between 2 pieces of metal. The intense friction generates heat, which softens the metal, but critically, it does not melt it. The metal just gets soft and kind of plastic-like. Second, during the traversing phase, this spinning tool moves along the seam, literally stirring the softened metal from the 2 pieces together. Finally, in the retracing, or stop phase, the tool just pulls out, leaving behind a perfectly forged solid-state joint. To truly appreciate how this works, we really need to look under the hood. Let's get inside the machine.
Section 5. The anatomy of FSW, inside the machine. The spinning tool is really the heart of this entire operation, and it has some very specific nomenclature we need to cover. First up is the tool's shoulder. This is the wider, flat part that rides right on top of the surface, generating friction and capping the hot metal so it doesn't squirt out. Below that is the tool pin, or probe. This is the part that actually plunges into the joint and aggressively stirs the material horizontally and vertically. Think of it exactly like sticking a spoon into thick dough or clay and stirring it up. Now, crucially, the dynamics of this stirring create 2 distinct sides to the weld. The advancing side is where the direction of the tool's rotation matches the forward movement of the machine. The retreating side is where the rotation opposes that forward movement. This dynamic creates an asymmetric flow of plasticized metal around the pin, making the actual design of the tool absolutely critical. Looking at these 3D renders, we can finally see exactly what these high-tech tools look like. You can clearly see that shoulder on top and the profiled pin extending out the bottom. On the right-hand image, you can even see a cross-section showing liquid cooling channels and thermocouple sensors built right into the tool holder itself. These aren't just simple drill bits, guys. These are highly engineered, incredibly robust instruments designed to withstand just unimaginable friction and force without breaking a sweat. And because these tools are non-consumable, meaning they aren't supposed to melt into the weld itself, the material they're made of must meet some extreme physical demands. The tool must possess high hot hardness, meaning it won't soften when the friction cranks the temperature way up. It needs immense mechanical strength and stiffness, so it doesn't just snap while plowing through solid steel or aluminum. It also needs high thermal conductivity to manage all that heat, a low coefficient of thermal expansion so it doesn't warp out of shape, and chemical inertness so it doesn't react with the metals it's joining. Honestly, selecting the right tool material is arguably the most vital engineering choice in this entire process. So, where is all this incredibly demanding engineering actually being used? Well, let's look at the future of joining through some truly epic applications. Section 6. The future of joining. Epic applications.
Friction stir welding isn't just some lab experiment. It is actively reshaping heavy industry right now as we speak. Consider this massive tube sheet heat exchanger. Historically, joining hundreds of tiny tubes to a massive thick plate using arc welding was incredibly tedious, super slow, and highly prone to tiny leaks due to porosity in the liquid melt pool. But with FSW, a machine can systematically plunge and stir each of these joints, creating flawless, defect-free, solid-state bonds that easily handle the intense pressure demands of the nuclear and energy sectors. It's truly amazing.
And this technology is also vital in an even more extreme environment, aerospace. When you're building space in aircraft structures, every single gram of weight and every microscopic fracture matters. The aerospace industry quickly adopted friction stir welding because it eliminates the melt zone entirely, massively reduces distortion, and guarantees zero porosity. In fact, the gigantic cryogenic fuel tanks used on modern space vehicles, like the Delta rockets, are now successfully manufactured using this exact technology. We are literally stirring the structural backbone of our spacecraft together. How cool is that? Which brings us to our final provocative thought. We've seen how solid-state welding, and specifically friction stir welding, eliminates the catastrophic defects of melting, drastically reduces energy consumption to a mere fraction of traditional methods, and creates impenetrable bonds strong enough for outer space. It really forces us to ask, as this green solid-state technology continues to advance and adapt to more and more complex alloys, will there ever come a day when we no longer need to melt metal to join it together? It's a fascinating question, and one I hope leaves you eager to learn more about the incredible manufacturing innovations shaping our world today. Thank you so much for joining me for this explainer, and hey, keep staying curious.